Hi everyone, we are Team 6. I'm Yang Peng.
M 一师，M 语同勤。
Now I will briefly present part 1 and part 2 of our forecasting project. First, I will talk about the time series description. We use the quarterly investment rate of growth from Denmark as our main variable. Overall, the series fluctuates around zero and does not show a clear long-term trend. Although there are some spikes, the values remain within a relatively stable range. Next, we divide the data into a training period from 1961 Q1 to 2020 Q4, and a testing period from 2021 Q1 to 2022 Q4. When we compare the fourth sample with the final period, we found that the patterns are quite similar, which suggests that the pandemic did not significantly affect the structure of the data. Then we look at the description statistic using the training period. The mean is close to zero, indicating no strong upward or downward bias, while the standard deviation shows moderate variability. After that, we analyze the ACF and the PACF. The ACF decreased gradually and the PCF shows a strong spike at lag 1. This pattern suggests that the series can be approximated by an AR1 process. We also performed the ADF test, and the result shows that the p-value are all below 0.05. Therefore, we reject the non-hypothesis and conclude that the series is stationary. Next, we test for co-integration. The John-Hansen test shows that two series are co-integrated, which means there is a long-run relationship between them. Then we test for Granger causality. The result shows that Q3 Granger causes Q1 at lag 4, which indicates a short-run effect with a delay of about 4 quarters. Now moving to part 2, which focused on ARIMA forecasting. Using automatic model selection based on AIC, we identified an ARMA 96 model as the best model. Then we use this model to produce forecast for testing period. The results show that the forecast follows the general pattern of the actual data, although it does not capture all fluctuation perfectly. The RMSE indicates that the model performs reasonably well. Finally, we re-estimate the model using the full sample and generate a new forecast for next 8 quarters. The new forecast is smooth and reflects the long-term pattern of the series, but it may miss some sudden changes. Overall, the ARIMA model provides a stable and useful benchmark for forecasting.
Now I will talk about question 3, forecasting with Gauge model. I use the data on Finland's investment growth. Firstly, we start with a Riemann model, and the model has an AIC is about 5.64, which suggests it's a reasonably good fit. Then we look at the residuals. They fluctuate around zero and don't show a clear pattern, so the Riemann model works well for the mean. But when we look at the squared residuals, we can see some clustering, which suggests that volatility may not be constant. Next, we run the arch test. At leg 1, the result is not significant, but at leg 4, it becomes significant. So it means volatility exists, but it shows up over multiple periods, not just immediately. Then we estimate the Gauge-1-1 model. The model is roughly constant term around 68.44, coefficient on past shocks about 0.14, and coefficient on past volatility about 0.59. So both past shocks and past volatility matters. Also, since 0.14 plus 0.59 is about 0.73, the volatility is quite persistent, but since it is still less than 1, so the model remains stable. After that, we use this model to make the forecast for the testing period. The testing period generally follows the real data, but it's not perfect. The confidence interval is quite wide, which shows there is still uncertainty in predicting investment growth. Finally, we re-estimate the model using all the data and make a forecast for the next 8 quarters. The future forecast looks relatively stable, but it shows some level of uncertainty. So it's done predicting large fluctuations, but it also doesn't assume everything is completely stable. So overall, the Gauge model helps us understand how volatility changes over time, and compared to ARIMA, it gives us more information about risk and uncertainty.
Okay, let's move to the fourth part, forecasting with VAR or VEC model. Here we use training period from 1961 Q4 to 2020 Q4. And this model is we estimate by using VAR model. Next, show and comment on the impulse response function. Here are the 4 pictures. We just use the impulse response function to analyze Q1 and Q3 both respond strongly to their own shocks, while cross-variable responses are positive but relatively moderate and weaken over time. Next, show and comment on the variance decomposition. Q1 and Q3 variance are mainly driven by their own shocks, with cross effects increasing slightly over time but remaining weak. Next, we produce a forecast called F3 for the first TI for the testing period and show RMIC. We can see the RMIC here, and the Q1 F3 shows a steady downward trend indicating a consistent decline over the forecast period. Q3 F3 increases initially and then stabilizes, suggesting convergence to a long-run level. Overall, the two theories exhibit different dynamics, reflecting varying responses in the model. Next, we re-estimate the VAR model. What's the difference is that we use the whole time period here from 1961 Q3 to 2022 Q4. Q1 F3R shows a gradual upward trend that stabilizes over time. Q3 F3R declines steadily and converges to a lower long-run level. Then we combined forecast here, F31, the combined forecast smoothes the fluctuations of individual forecasts and lies between F1, F2, and F3. It follows the general direction of the actual series, but still misses some turning points. Overall, FCF provides a more stable and balanced prediction than the individual models. Then we use 8 quarters after the original data set, compute combined forecast called CIFR here. We can see that the period is 2023 Q1 to 2024 Q4, but the software always quit when I drag it into 2022 Q4. Therefore, we can see that there are some data about 2024 to here, and I put this picture on. Overall, the combined forecast provides a more balanced and less volatile prediction. Okay, thanks for your listening.